Okay, a good and rainy morning, everybody. Ang sarap matulog sana, no? Kaya lang we don't have any choice. But it's 8:30, so it's Math 174 time. This would be our probably what? Medyo mahaba pa pala. I think we still have at least 3 meetings left to finish the 11 modules. We are on module number 10 right now, the second half na nung module na to. But just while I'm fixing my screen, kailangan ko munang umadlib. But anyway, housekeeping matters muna tayo. I already made available problem set, no, not the problem set, but laboratory exercise number 6. That will be either the last or the second to the last. But I'm thinking it's more of the second to the last laboratory exercise. So you can check Canvas out. It will be due originally December 9, which is on Monday. Sorry, not December 9, December 12, which is on Monday. Pero nangako pala ako sa inyo last time. Thank you for those who reminded me that I told you that the deadline would be on December 19th. But don't fall into the procrastination trap. Ano? Kasi there could probably be another another lab exer that will be due on December 19th. Pero hold on, let me see. Let me think about it. Okay. All right. Maybe, sige, final na. So, laboratory exercise number 6 will be the final laboratory exercise for the semester. All right, okay lang ba yun? And then whatever we'll discuss on module number 11, which is Monte Carlo simulations, that will be the third problem in the problem set. Ano, para medyo hindi masayang yung pag-aaralan natin next week, which is a very nice integration method. So ang gagawin natin, yun yung number 3, yun yung problem solving item sa problem set number 3. Number ano na ba tayo? Number 2. All right? So para alam nyo na rin yung paghahanda nyo at saka para magkaroon siya ng ng commensurate rate dun sa inyong grade. So siya solely yung nandun sa item number 3 sa problem set. And in my experience, madalas yung nasa module 11 yung ginagamit sa final project. So I think it's fair na wag na tayo mag-lab exer for module 11 because after all, I'll be asking you a lot of things about it in the problem set, and there's a big chance that you're going to use it for the final project. Which reminds me, I already uploaded a sign-up sheet for the final project. So if you're looking for a group, for group mates, so kindly sign up dun sa Google Doc na yun na sinend ko via email or via Canvas announcement. If you miss it, you can go to the announcements page in Canvas and then search for the latest announcement that I posted. So dun yung mahanap yung Google Sheet. Kung kompleto na yung group nyo, hindi nyo na kailangan magsagot dun sa sign-up sheet. Just communicate with each other, and then I'll just learn your grouping pag nagpasa na kayo ng final project. Tapos, but if you want to work solo, that's fine. So wala ka nang gagawin, mag-work ka na kagad. But say tatatlo pa lang kayo and then you want a 4th member, sign up on the Google Doc and then indicate that you want 4 members or you're looking for another one so that your classmates will know na pwede pa silang sumingit dun sa group nyo. Tapos common courtesy na lang natin kung sino yung pinakahuling nag-sign up, siya yung ko-contact dun sa mga members, sa existing members ng group para malaman nila na may sumali na sa atin so we can move on with the division of labor. Okay. I'll post the final details for the final project next week kasabay nung pagbibigay ko nung huling problem set. The last problem set will be due officially December 21st, the last day of classes, but I can give you some more days to finish it, probably hanggang December 24, 11:59 p.m. para after Noche Buena, pwede na ako mag-start mag-check. But I encourage you guys to submit as early as you can para rin mas mabilis ko silang mag-gradean. The final project will be due on the last day of final exams, which I think is on January 11. So you will still have ample time to do the work. Sarap talaga ng scalding hot coffee. But anyway, So let's continue module number 10. So last time we looked at Romberg integration, which is an application of the Richardson extrapolation technique to the composite trapezoidal rule, because the composite trapezoidal rule is an ordered h squared formula. So order 2 siya, big O of h squared yung error niya. So what we discussed in numerical, our exemplar or our example when we talk about numerical differentiation techniques ay nag-apply pa rin dun sa composite trapezoidal rule, and that was what exactly was done to get the Romberg integration formula. In your laboratory exercise, I ask you to determine how many rows of the Romberg integration tableau is needed in order to achieve a convergence tolerance, or what we call the relative computable error estimate. Di ko to nabanggit last time, pero binigyan ko pala siya ng pangalan in the module. So it is the ratio that you see in equation 10.1 is what we call the relative computable error estimate. Unfortunately, we don't have a closed form formula for the relative computable error estimate in terms of the number of rows in. So in the laboratory exercise, what you'll need to do is to perform the Romberg integration row by row. Okay? Tapos i-check nyo yung RNN. So yung mga diagonal entries ba, na-satisfy niya na yung nabigay na value ng relative computable error estimate na nandun sa exercise. Okay? So you don't need to do or to research or to derive an analytic way to find n given the value of epsilon on the right-hand side of this inequality in 10.1. All right. So gagawin nyo lang yung Romberg integration tableau line by line or row by row, and then check, is this met for that particular row number? Pag hindi, pupunta ka sa susunod na row number. And you will experience firsthand kung bakit natin sinabi na highly extendable yung Romberg integration process, because we are just adding some rows to it without too much complications of, say, kung Newton codes yung gagamitin mo, pag nag-add ka ng isang point, you'll need to redo all the computations, including the interpolation. So medyo mabigat sila. Pero yung Romberg integration, parang ito yung parang Lego ito. So you just add some more steps whenever you needed. Okay. Now, in this, the Romberg integration addresses some of the problems or some of the shortcomings of the numerical quadrature rules, specifically the pessimistic bounds. Because when you're working with pessimistic bounds, you are bound to make to do work or to do more work than what was required to get the level of accuracy that you had in mind. Okay. So ito sa Richardson extrapolation, talagang ginagawa mo lamang yung kailangan mong gawing work, right? So ito yung work smarter than working harder. Okay. So that's it. If you have any questions, just send me an email about the problems, the lab exer. I encourage you to try to finish it by Monday. Kung wala kayong exam ng 151, so kindly finish it on Monday para hindi na kayo matambakan week after next. Kasi though sabi ko nga wala ng lab exer week after next, pero you should be starting with the problem set. And I know you have lots of things on your plate right now. Sabay-sabay ang mga deadlines na yan. So kindly plan your work. Okay, so today we'll just continue with the rest of the modules, and here we'll be talking about integration anomalies. So it seems that we have created a sort of robust and a strong integration theory in terms of numerical quadrature formulas, be it Newton codes, be it Gaussian quadratures. Ang dali na nilang ma-derive. Hopefully, madali siyang naintindihan. Yung continuum problem na nag-integrate tayo ng napakahirap na function little f. Ang hirap hanapan ng antiderivative or walang antiderivative at all. Kaya pala natin siyang i-approximate using a linear combinations of the function values themselves. So medyo napagaan yung proseso. And we have found ways to accelerate the convergence of the estimates obtained from this numerical quadrature formulas via Richardson extrapolation. So what else could we ask for? Ano, parang ganun yung datingan. Pero like anything in life, parang wala naman perfectong bagay. There would be some problems along the way. And as numerical analysts or as mathematicians, it is our goal to better improve yung mga existing methods. Because sooner or later, we'll encounter some functions that are naughty na hindi nag-apply or hindi magpe-perform as expected yung mga dinerive natin o mga dinevelop natin na integration formulas. All right? A quick example is the square root is the integral from 0 to 1 of x to the 2/3 dx. So it seems to be a very simple function. It's elementary because there is a closed form antiderivative for it. All right. So since continuous yung function, nag-exist naman yung derivative niya, madaling kunin yung antiderivative niya. Actually, the antiderivative is also smooth because the antiderivative of x to the 2/3 is what? X to the 5/3 all over 5/3. So continuous pa rin yun all throughout the interval 0 to 1. Actually, it's continuous everywhere. So we don't expect any complication when we apply our numerical integration formulas. Actually, there's no need for them because you can simply use the second fundamental theorem of calculus to get the exact value. Pero itong simpleng integral na to, pag pina-integrate ko to dun sa mga quadrature formulas natin, the quadrature formulas will fail to perform as expected. Yun yung isa sa mga tinatawag kong integration anomalies. There doesn't seem to be a big problem with x to the 2/3. It's antiderivative, it's also continuous, it's smooth. It should work perfectly. But if we do an empirical test, meaning I will run, say, the trapezoidal rule, the Simpson's rule, the midpoint rule, and the two-point Gaussian rule with various number of discretization points used. Oh, by the way, ito ay mga composite rules. So gumamit ako ng 2 points para sa composite trapezoidal, composite Simpsons, composite midpoint, and composite two-point Gaussian. Ito yung mga errors na makukuha ko. And then I continue taking half of the step size or doubling the number of points used in each of these composite methods. Tapos, tinake note ko yung mga errors. So meron ako ngayong table ng mga errors. Now, I took note of what is the empirical order of convergence or the EOC and compared it with the theoretical order of convergence or the TOC. Remember, dun sa derivation natin, yung composite trapezoidal rule ay order of convergence big O of h squared. So that means ang theoretical order of convergence niya ay equal kay 2. What does that mean? Well, that means that h squared is an asymptotic upper bound of the error term. Kasi sabi natin yung error function as of the error as a function of h is a big O of h squared. So that means in theory, there exists a constant m and a value h sub 0, okay, greater than 0, such that ang e of h, ang absolute value niya, ay bounded above by the constant m times h squared for all h greater than h sub 0. That's the very definition of the Bachmann-Landau notation big O. All right? So yung ibig sabihin niya, or equivalently, that means that the limit of the absolute value of the error term all over h squared as h approaches 0 must be equal to a constant m or the constant m. So dito natin natetest yung error, dito natin natetest yung order of convergence. Ang hirap magklase kapag mas masarap matulog, ano. Biglang lumilipad yung utak ko. But anyway, this is the limit that we need to check. So if you want to get empirical evidence of the order of convergence, well, you need to perform or to apply the the numerical formulas with varying values of h. Actually, mas okay pala kung h yung dinisplay ko rito, no? Dapat h yung dinisplay ko rito. So dito ang h natin ay 1 kasi ang ating interval ay 0 to 1. So hatiin ko yung interval into two subintervals, or actually into two discretization points that will give me one big interval which is of length 1. Pagka meron akong n equals 4, that means that meron akong 4 na points. So ibig sabihin, the step size is 1/3. Kasi kung meron akong 4 na points, 0 to 1, tapos meron pa ako dito, meron ako dito, this is my x1, this is my x2, meron akong 4 na points. So ibig sabihin, hinati ko yung interval sa 3. So that means I'll have 1/3 there as my step size. And then I'll have 1 over 7. And then I'll have 1 over 15, 1 over 31, 1 over 63. Yan yung mga step sizes, right? So to get to check, well, what's the empirical order of convergence, right? Based on this data, kailangan ko lang kunin yung limit ng, tingnan yung limit ng error divided by h squared as h approaches 0. In case of discrete data, kailangan ko lang kunin ito. Oops, sorry. Ito. I-divide ko siya by h squared. Titingnan ko kung magko-converge yan sa isang constant. Alright? So, pag kinuha nyo to, 3.502 times 10 to the negative 2 divided by h squared, you tally the number. This divided by 1/3 squared, you tally the quotient. This guy divided by 1 over 7 quantity squared, you tally the quotient, and then you should get a sequence of quotients that approach a constant. Pero ginawa ko to sa Excel kanina. Pinaglaruan ko siya sa Excel. So yung unang quotient, pag dinivide ko by h squared, of course, it's 0.03502. This guy divided by 1/9 is 10737. This guy divided by 1 over 49 is 0.19, then 0.29, 0.41, 0.54. It doesn't seem to converge to a constant. Parang siya ay nag-i-increase. Alright? So, ibig sabihin, parang increasing yung trend kapag kinuha ko itong mga to, dinivide ko by h squared. So, that means there's an increasing trend. Ito yung quotients na kinocompute ko. So, ibig sabihin, parang mas mabilis lumaki yung absolute value ng error than h squared. Kasi pag ito, dinivide ko by the corresponding value of h squared, parang mas lumalaki yung quotient. So that signifies na mas mabilis lumaki yung error kaysa sa h squared, which doesn't make sense because we said that the error theoretically of the composite trapezoidal rule is of order big O of h squared. Dapat magkasing bilis lang sila halos ng h squared nag-approach ng 0. But that's not the case with this empirical evidence. So hindi niya na-achieve yung theoretical order of convergence na 2. Then you'll need to search dahil yung quotients, itong mga quotients na to ay hindi nag-approach ng isang constant pero increasing yung trend. So that means yung exponent kailangan kong babaan. Right? Kasi mas mabilis siyang lumaki kay h squared, so dapat mas maliit yung exponent ni h squared. And true enough, if you do an exhaustive search, though I won't ask you to do it kasi medyo kakaibang numerical technique or theoretical technique yung kailangan para mahanap yung empirical order of convergence, ang nakuha ko ay 1.5986. That means kapag kinuha ko yung error divided by h to the 1.5986, that's when I will get a constant value. Nung ginawa ko to sa Excel, parang 0.10 yung constant na yun. Right? So that means the errors divided by h to the power 1.5986 approaches a constant 0.10. That's what we call the asymptotic error constant. All right? So that signifies na magsing bilis lang si h to the 1.5986 at saka yung error nagva-vanish papunta sa 0. So that means ang order of convergence based on our empirical data is just 1.59. Mas mababa kaysa dun sa pinangako ng ating derivation. So that means there's an underperformance of the composite trapezoidal rule for this very seemingly simple integral. Right? So ito yung ito yung anomaly. Bakit kaya nagkaganon? Hindi siya naging order 2. Na dapat order 2 siya. Medyo malaking discrepancy. Okay lang sana kung order 1.99, order 1.92, pero order 1.59, almost 25% yung nabawas sa theoretical order of convergence. So that's our goal for this meeting, or nakakalahati na pala kagad ako ng klase. Titingnan natin kailan nangyayari itong mga anomalies na to at ano yung mga paraan para ma-improve yung numerical implementation ng numerical integration formulas. In other words, we want to eliminate the anomaly. Eliminate the cause of that anomaly so that our numerical integration techniques can function as expected. And you will see, ganun din yung nangyari dun sa ibang mga quadrature rules sa Simpson's, midpoint, and Gaussian. Lalo na yung Simpsons, ang laki nung nasuffer nung Simpson at saka nung 2-point Gaussian. Because theoretically, they should be of order of convergence 4. Pero yung Simpsons, pumalo lamang sa 1.66. Yung 2-point Gaussian, pumalo lang ng 1.66. So para bang na-scam tayo dito, ano? So ang nasa sabi ng seller ng Simpsons, ang theoretical order of convergence ay 4. Pero nung nakuha nyo na yung parcel, nung tinest nyo siya, 1.66 lang yung nabigay. So what's the anomaly? What's the scam here? The problem is, x to the 2/3, although it possesses a closed form antiderivative that is smooth, hindi kasi sufficiently smooth yung function x to the 2/3 itself. Because remember, the trapezoidal rule, the Simpson's rule, and the other rules are actually derived from the Taylor, what you call this? Or their error depends on the derivative of the function. And if your function is not infinitely smooth, meaning continuous dapat lahat ng derivatives niya, there's some point na hindi na magiging smooth, or hindi mag-exist, or hindi magiging continuous yung derivative. That means that the error estimates that we derive, the theoretical error estimates that came with our formulas will not apply. Kasi nga kailangan maraming derivatives ang nag-exist para dun sa ating function. Pag kinuha nyo yung derivative ng x to the 2/3, kasi remember, pag nag-Newton cotes ka, or nag-interpolate ka lang naman, tapos yung interpolant, yun yung ginagamit natin sa integral. So yung error doon, nakadepende dun sa error sa interpolation. Pero yung error sa interpolation requires a higher order derivative, right? Ito yung error sa interpolation. Meron kang n plus first derivative. Now, tingnan niyo yung x to the 2/3. Pag kinuha niyo yung first derivative niya, maging x to the negative 1/3, and x to the negative 1/3 doesn't exist at x equals 0. Or there's a blow up when x approaches 0. Nag-approach ng positive infinity kapag kasi x ay nag-approach ng 0 from the left. So that will cause a blow up dun pa lang sa first derivative of the integrand, right? Tapos pag kinuha mo pa yung second derivative nun, x to the negative x to the negative, x to the negative 1/3, so x to the negative 4/3, and so on. So mas bumibilis yung essential discontinuity, or nagiging steep yung essential discontinuity as x approaches 0. And di ba kinukuha natin yung maximum ng absolute value ng isang mataas na derivative ni f para makuha yung error sa interpolation. And nakita natin yung mga derivatives ng integrand ay nag-approach ng infinity as x approaches 0. So kaya nagbe-blow up yung error. Okay? Now, what can we do about this? Should we just go to the corner and cry? Mag-walling na lang ba tayo? Ano? Hindi. There are some analytical techniques, some pre-processing techniques that we can apply to the integrand itself to avoid the underperformance of our numerical integration routines. In particular, for cases like these, when you have fractional exponents, kasi pag fractional yung exponent mo, sooner or later, pag nag-differentiate ka, di ba, pag nagde-differentiate tayo, nagma-minus lang naman tayo ng 1 paulit-ulit dun sa exponent. Tapos bumababa siya later. So essentially, lumiliit ng isa yung exponent ng x kapag ka nagde-differentiate ka. So kung fractional yung exponent, when I say fractional, pwede ring mixed fraction. Basta pag hindi integer yung exponent, magma-minus ka ng 1, sooner or later, magiging negative yon. Right? Hindi natin yung problema sa x to the power n, where n is an integer, kasi kapag pag nag-differentiate ka na ng x, ang sagot na ay constant, derivative ng constant, 0, so all throughout, magzi-0 na yung derivative niya. So hindi ka nagkakaroon ng blowing up na derivative. Pero pag may fraction sa exponent, doon posibleng magkaroon ng negative exponents yung mga derivatives, which will cause a blow up, especially if 0 is part of the integration interval. All right? So anong remedyo doon? Well, get rid of the fractional exponent. Do a proper substitution so that x to the 2/3 will be expressed in terms of another variable but raised to an integral or an integer power. Typo, there should be a dx there. Okay? So ano kaya yung tamang substitute? X to the 2/3. So what should be our proper substitute para mawala yung exponent na 2/3? Of course, there are several ways on how to do it. Pero what do you want? Yung pwede natin gawin. Hoy guys, nandiyan pa ba kayo? So ano kaya yung substitution? Oh, no peeking dun sa solution. U equals 2/3. Kung ilalat ko na yung u ay 2/3, ang du ko ay magiging 0, wala akong magagawa doon, Victor. Kasi di ba pag nag-let u ka doon sa integral, magkakaroon ka ng du dapat kasi mag-i-integrate tayo with respect to u. So hindi pwedeng mag-constant substitution. So it's a change of variables. So u equals something involving x, but what should that be? Kasi ang goal ko lang talaga mawala yung exponent eh. Or either you let u or you change x. So alin dito? Sige. Ano dapat yung substitution? Isipin niyo muna habang mag-inom muna ako ng kape. Mukhang mas madali ay, anong mas madali? Mukhang mas madali ito. Palitan natin si x. Parang algebraic substitution na ginamit nyo sa Math 36. Well, yes, you can let u to be equal to x to the 1/3. Okay. Bakit nyo gagawin yon? Because if if u is equal to x to the 1/3, then yung x to the 2/3 ay magiging u squared. You will be free of and then we'll do the integration with respect to u. You'll be free of the fractional exponent because you'll have a polynomial u squared as your integrand, which is infinitely smooth. We won't have any problem with it, and it will fit perfectly doon sa konsepto ng Gaussian quadratures. Kasi yung Gaussian quadratures, designed sila to get the best approximate for the integrals of polynomials, right? Kaya lang, Pag kinuha natin yung du, kasi pag nagpalit tayo ng variable, dapat magpapalit din tayo ng differential, right? So if I will get the derivative of u based on this suggested substitution, I'm gonna get 1/3 x to the negative 2/3 dx. So that means, actually pwede rin pala, no? That means I'll have 3 du x to the 2/3 equals dx. So ibig sabihin yung dx ay mapapalitan ng x to the 2/3. Tama ba? 3 du x to the 2/3. So itong dx na to, mapapalitan nitong guy na to. Kaka-problema pa rin pala ako. Hindi ko magagawa ng maayos yung substitution, right? So I cannot get a nice looking expression for the integral. It's as if if I carry on with this substitution, everything will be messed up. Tama ba? Or mali lang yung computations ko? Tama, no? Ang du ko ay 1/3 x to the negative 2/3 dx. So ibig sabihin, para magkaroon ako ng du, kailangan ko ng x to the negative 2/3. But I don't have an x to the negative 2/3 in the original expression. Okay, so that means this is not a good substitution. Kaya sabi ko medyo mahirap yata yung substitution na to. Baka pwedeng maging u squared yung x to the 2/3. Yeah, I think that's what can be done, right? Pero okay, let's see. U cubed. This is what I have in mind probably. I can let x be equal to u to the 2/3. Sorry, x equals u cubed. Ito yung suggestion kanina ni Ray. Or similar dun sa suggestion ni Kiefer to let u be equal to cube root of x. But I really don't want to work with n roots. Kasi nga, pagka nag-n root ka, lagi kang magkakaroon ng fractional exponents pa rin. So let's keep it as close to polynomials as possible. But Ray's and Kiefer's suggestions are good. I'm thinking kung yung kay Neo ay pwede rin. Pero you can try Neo. If that substitution can give you an integral of a polynomial in u, then that's fine. Okay. Pero let's do this. X equals 2/3. Then that means okay lang kasi yung x to the 2/3 ay magiging what? Niraise ko kay 2/3, so x to the 2/3 will just be equal to u squared rather. And then ito pala, tama. Ito rin pala yung sinasabi mo, Neo. Ito rin yung mangyayari, right? So yun. And then the only constraint is, do I get the right change in the differential as well? So if we'll compute dx from here, we'll get 3u squared du. And this is in a much nicer form than the previous substitution that we had, because this is telling us that dx should be replaced by 3u squared du, right? So si dx magiging 3u squared du, si x to the 2/3 mapapalitan ng u squared, then we need to change the bounds as well. This is a bound x equals 0, so when x is equal to 0, u is equal to 0, so lower bound pa rin natin ay 0. Tapos when x is 1, that means u is equal to, ano ba yung u natin? Si u ay equal sa cube root ni x. So when x is equal to 1, u is still equal to 1. And that's perfectly fine. So that means after this substitution, we're going to get an alternative form for a, which is the integral from 0 to 1 of 3u to the 4th du. And the amazing thing about this is that very simple algebraic substitution will restore the performance, or the expected, will restore the performance of our numerical integration formulas to what was intended, or to what they were designed. Okay? So makikita nyo, ginawa ko ulit, nirun ko ulit yung composite quadrature rules, pero this time, for this representation for the integral a, it's the same integral, it's the same value, but in a different form. So parang naganap tayo ng isang function na kaparehas ng integral ng x to the 2/3, pero mas maganda dapat yung form ng function na yon. And this is really better because this is, I guess, the best that we can get because it's a polynomial. So pag nirun ko uli yung apat na composite rules, take a look at their EOCs, compare it with their TOCs, they are now back to optimal shape. All right? Na-restore na natin yung order of convergence. Okay? Isn't it amazing? Or ako lang yung natutuwa? Lumalabas tuloy yung pagka-nerd mo. Okay, let's look at another example. Of course, there are some more issues. Ano? Unang-una na tong fractional exponents. Pero may isa pa. Punta natin yung mga improper integrals naman. So, kapag meron kang improper integrals, malaking problema yan. Actually, hanggang ngayon, sa actual research na ginagawa ko, meron kaming mga functions na discontinuous or may essential or removable discontinuity na gusto naming i-integrate numerically. Kasi pagka nagmo-model ka ng sound waves, may mga functions na nagpa-pop up na essentially discontinuous. Pero gusto kong mag-integrate, syempre hindi ko siya i-integrate by hand kasi komplikado mga function yon. So mag-Gaussian quadratures ako. Pero to prevent instability and inaccuracies in the Gaussian quadrature, I need to think of some clever ways on how to package the integral before giving it to the quadrature rule para ma-ensure ko na magko-converge yung value ng integral. Alright, yun yung titingnan natin sa mga susunod na examples. The first one is an easy one. It's just a removable discontinuity. So meron kang function e to the x minus 1 over x, and then you want to integrate it from -1 to 1. You see right away that this is discontinuous at x equals 0, which is part of the integration interval, kasi meron ka na kagad 0 sa denominator. So that means there is a very big chance that your numerical integration routines will not function well for this integral, especially if 0 happens to be one of your discretization points. Kasi wala kang function value na makukuha, or if your function value is very, very close to 0, actually, hindi pala. Okay lang kung malapit na malapit siya sa 0. Basta kapag si x ay naging discretization point mo, magkakaroon ka na ng problema. Now, how do we get rid of this removable discontinuity? Well, kapag removable yung discontinuity, tanggalin mo lang talaga yung discontinuity. So remember sa math 36 ba yun? Pinag-check kayo kung removable o essential yung discontinuity. Tapos, if it's removable, then make it into a continuous function. Redefine the function to make it continuous over the given interval. So dito naman natin magagamit yung tinuro sa inyo sa Math 36. Kasi kapag na-turn natin itong function na to into something that is continuous all throughout the integration interval, then we got rid of one of the anomalies involved, right? So first, check if your integrand is really removably discontinuous, right? Removable yung discontinuity niya kasi kapag kinuha mo yung limit in the f of x as x approaches 0, you'll just need to apply L'Hopital's rule at makukuha mong value ay equal kay 1. Nag-exist yung limit, yung function value ay hindi nag-exist. So to remove the discontinuity, simply redefine f into a function, say f hat, such that the value at the point at which the function is not previously defined will be set to the limit, right? So limit ay equal kay 1. So gawin ko na lang 1 yung function value ni f kapag si x ay equal to 0. So hindi na siya undefined kay x equals 0. Meron na siyang value na assign natin, which is equal to 1, which is essentially the limit. Okay? And then you'll just need to pray that after this redefinition, mag-work na optimally yung aking integration quadrature formulas. Kasi sana wala na siyang ibang problemang ma-encounter. Alright? Kasi posibleng hindi lang isa yung problema, pwedeng patong-patong sila. Like, halimbawa, fractional exponents, mag-occur uli siya. So you have to remedy the fractional exponents as well. Okay? So ito yung general template. Kapag removable yung discontinuity, just remove the discontinuity by redefining the function f into a continuous one. All right? Next example, ito yung sinasabi ko kanina na combo. Una, ito ay merong removable discontinuity. Sin x over x dx, obviously, it is undefined at x equals 0. Pero pag kinuha mo yung limit of f as x approaches 0, equals siya kay 0. So what we could have done is to redefine the function so that it will be continuous at x equals 0. So ibig sabihin, i-assign ko lang yung function value ng sin x, ng function ng integrand natin to be equal to 0 when x is equal to 0. Kasi yun yung limit niya. Right? Kaya lang, pag ni-redefine ko yung function, magkakaroon pa rin ako ng problema. Kasi itong sin x over square root of x also suffers from fractional exponents. It doesn't seem so, pero pag kinuha mo yung Maclaurin series expansion ni f, ito yung makukuha mo. So expand mo yung sin x using Taylor's theorem with a equals 0 sa Maclaurin expansion divided by square root of x. Tapos pag sinimplify mo yan, ito yung makukuha mo. So our function f involves fractional exponents. And again, pag meron kang fractional exponents, mag-underperform yung ating integration routine. Kasi nangyayari ron, pag nag-differentiate ka, may chance na maging negative yung exponents ni x, yun yung nandun sa error bound. So for sure, mag-blow up yung error, at least yung upper bound natin sa error, so nagiging unbounded yung error natin. So that means posible talaga mag-underperform yung numerical integration formula kasi yung itsura ni f ay isang infinite series ng powers ng x to the something over 2. Meron kang fractional exponents. Now, so babalik tayo dun sa una nating example. Kailangan nating tanggalin yung fractional exponents. And the key here is dahil 2 yung denominator na yan, or 2 yung denominators nilang lahat, gusto kong palitan si x ng isang variable na merong even power. Right? Kasi kapag ginawa kong x equals 2 to the n, right? So, yung mga x's mapapalitan ng 2 ng u to the 2n, tas pag divide ko sila by 2, mawawala na yung fractional exponents kasi makakancel with the 2 that I introduced for the variable u. But why will I choose a large value of n? Gamitin ko na yung pinakamaliit na value in n. So gawin ko lang kunwari, si x ay equal kay u squared. So that means this guy will be just u. This will be what? This will be u to the 5th. This will be u to the 9th, and so on. So lahat sila maging integer na yung exponents. There are some constants involved, but that's fine. And then u squared ay x equals u squared. Ang dx lang naman dyan ay 2u du, right? So yung dx, papalitan ko lang ng 2u du, I'll still get the polynomial. And that should have been fine, right? Pero wag kayo dito sa Taylor series expansion magano. Kung pwedeng hindi sa Maclaurin series expansion mag-integrate, then go back to your original problem, right? And that is true in this case. X equals u squared. Gamitin ko yung substitution dito. Luckily, na-solve natin in one fell swoop, pati yung una nating problema. Because when you do the substitution x equals u squared to the original integral b, we will get this guy, which is infinitely smooth. Kaya lang sin u squared, wala yata itong closed form antiderivative, so we don't have any choice but to perform numerical integration. Okay? So, pinaglaruan ko to, or hindi ko alam kung ako yung nagawa or nilift ko doon kay Brady na book. Kapag gumamit ka ng 3-point Gaussian quadrature rule with the new integral, 87 evaluations lang yung kailangan mo. Pero kung to get the tolerance 5 times 10 to the negative 11. Pero kapag dito ka nag-work sa original integral na to, you will still get an accurate answer. 5 times 10 to the negative 11 yung threshold, makukuha niya yon, pero kakailanganin mo ng 677 function evaluation. That is around what? It is around 80 times yung kinailangan after the substitution was carried out. Okay? Kaya ang laking tulong na ina-analyze mo, hindi lang tayo, kasi mathematicians tayo hindi tayo mga computer scientists o mga applied scientists na kumukuha lang ng black box na parang bumibili ng isang appliance mula sa isang numerical integration store. Tapos may function ka na ginagamit mo sa research mo, ipa-plug in mo lang siya doon. Tayo hindi. Niluluto natin yung techniques o yung methods to suit our problem. Or we precondition the problem. We prepare our problem so that the appliance that we have will perform optimally. Right? So ganun tayo mag-isip. Hindi lang tayo apply ng apply. So titingnan natin ano yung implications. Alright? Suitable ba yung ingredient ko dun sa aking method? If not, I will precondition or I will pre-process my ingredient so that it will fit properly dun sa ating method na gagamitin. Okay? And then there are some more examples here. I hope to give you as much as possible. Pero in case we don't finish everything, so I'll put them as your reading assignments na lang. So yung mga susunod ay mga essential discontinuities naman. Yung mga essential discontinuities nangyayari kapag hindi continuous yung function mo kasi hindi nag-exist yung limit. Right? Now, how can we remedy cases like these? Halimbawa, ito. May dalawang klase kasi. Una yung algebraic essential discontinuity. So let's see this one. We say that there's an algebraic essential discontinuity if your function behaves like x minus a to the negative alpha for some positive alpha. So kung ganyan yung performance niya as x approaches a, then magiging positive or negative infinity yung limit. Kaya nangyayari yung essential discontinuity, right? An example is this guy, this very complicated guy over here. Pag kinuha mo yung limit niya as x approaches 0 coming from the right, kasi nga interval 0, 1 lang tayo, so there's only one way to approach 0, and that's coming from the right. If you compute for its limit, you're going to get negative infinity. So you cannot remove the discontinuity. Hindi gagana yung kwento ko kanina na i-redefine nyo lang yung function f, and then after that, try to remedy the other sources of anomaly, right? Pero rito wala tayong magagawa, negative infinity yung limit. So ibig sabihin, ang ibig sabihin nito, kapag pumili ka ng isang number na napakalapit kay 0, pagkasama siya sa iyong discretization points, isang napakalaking number yung makukuha mo. And that napakalaking number might ruin the entire approximation process. Okay? Now, one way to do this is to analyze how your function behaves or how this function looks like. If it looks like this guy, then we can perform a substitution that might lead us to a better form, to a better integrand. Okay, so if we take again the Taylor series or the Maclaurin series expansion of the functions involved in the integrand, meron no x to the negative 2/3 dyan. Wala na yung series expansion, so let's just leave x to the negative 2/3 there. Expansion ng cosine of this guy is that. Expansion ng e to the root x is this guy. And expansion of this guy is this guy. Or expansion of 1 over this guy ay ito. Okay? And then perform the calculations, you're gonna get this guy. Right? And so on. Marami pa yung kasunod. Pero what we observe here is that we have fractional exponents, right? And the problem really occurred here. Kaya siya nagbe-behave like x minus a, or in this case, our a is 0. It behaves like x to the negative alpha, where alpha is equal to 4 over 15. Kasi nga itong term na to, kapag kasi x ay 0, wala tayong problema sa mga to, kasi 0 lang yung values nila, pero ito palang term na to yung nagda-drive ng essential discontinuity. Alright? So there's a fractional exponent. So siguro yung fractional exponent muna yung itry nating sagutin. And I'm hoping that the problem will be solved by doing or by removing the fractional exponents. We see here that at least the first few terms ay naka-over 30. And I don't care about the last few terms because they will be insignificant compared to these terms. And actually, the problem only happens from the first term. So drawing up inference from this Maclaurin series expansion, or the first few terms of that expansion, I see that I can let u equals 30. if I will let u equals 30, then this will be gone. Pero magkakaroon pa rin ako ng x to the what? X to the negative 8. Right? But I'm praying na masolusyonan na to after I do the substitution. Kasi kung hindi, kailangan ko pang humanap ng iba pang substitution. All right? And then I'll be able to also eliminate the fractional exponents from these guys over here. Okay. Now, pag ginawa niyo yung x equals u to the 30th, pero do it here, all of those square root of x's will be gone. Okay. Kasi nga si x ay u to the 30, so parang least common multiple lang siya ng 5, ng 3, at saka ng 2. Mawawala yung mga square root dyan. And remember, ang mga square roots, sila yung nagbibigay, ay yung mga roots, sila yung nagbibigay sa atin ng fractional exponents. So when you perform that substitution, you'll get this nicer looking integral, right? Tapos nawala na ngayon yung essential discontinuity. Bakit? Kasi nagkaroon ka ng 1 plus u to the 10th. After the substitutions were all carried out, you had a 1 plus u to the 10th in the denominator. U to the 10th is always non-negative. Add 1 to it, so you'll get a positive number. So this being positive, hindi siya ever magzi-zero. And so this guy is continuous everywhere, including, of course, the interval 0 to 1. And so we are hoping now that this will be, this will be a nice input to our numerical integration formulas. And I don't see any problem with this. Kasi e to the u to the 10th, 1 plus u to the 10th. Yeah, kasi yung denominator mo ay never naman magzi-zero. So yung mga derivatives niya laging mag-exist. So that should be fine. Now, there are other examples over here. So I'll just assign them as reading assignment. So infinite bound, yung example 10.7, tapos 10.8, infinite bound plus the continuity, infinite bounds. May isa pa eh, ito pala. Yung logarithmic essential discontinuity naman. So I'll just put examples 10.6 until 10.9 as your reading assignments. Pero yung lab exer, meron siyang isang part na i-identify nyo muna yung anomaly. Actually, that's the first question. Then, perform the necessary substitution to remove the anomaly. Tapos saka pa lang kayo mag-Romberg integration. Right? So kindly play with it and see if it will be similar to one of the examples here. But just a caveat, itong examples ito ay non-exhaustive. Ito lang yung mga usual, ay yung mga madaling ma-spot na integration anomalies. There could be some anomalies not in this list, and it really takes some instinct para malaman ano dapat yung paraan para mawala yung mga discontinuities na yun o yung mga anomalies na yun. So you get to encounter this kind of things, and that will require you to be ingenious and creative with the workaround there. Okay? Nakita ko yan sa engineering, ang galing nila. Meron silang mga methods, nagsiseparate sila ng integrals para matanggal yung singularity. So you learn along the way. Kasi minsan wala sa libro yung mga discontinuities, so yung mga anomalies na makikita nyo. All right? But at least for our course, you are introduced to the basic anomalies, and then try to read the rest and then answer the laboratory exercise. Okay? So I'll stop here. Do you guys have any questions? So if there are none, don't forget to answer the sign-up sheet if you're looking for a groupmate or groupmates. And also don't forget to evaluate me and your lab instructor sa SAIS. The deadline is 9 p.m. I think the deadline is today, December 9. Ito yung usapan natin, pag hindi kayo nakasagot, pag hindi nyo nasagutan yung evaluation kay SAIS, automatically, syempre, hindi naman kayo magsasagot ng yes kay Canvas, So 0 kayo dun sa 5 points para sa final project, right? It's 5 points sa final project, so malaki siya. Hindi na kayo makakauno sa final project pag hindi kayo nag-evaluate. So go to SAIS as soon as you can And then after you go to size and evaluate me and your lab instructor, go back to Canvas, answer yes dun sa quiz. Right? Pagka nag-evaluate kayo pero hindi kayo nag-yes kay Canvas, 0 pa rin. Because I won't have any basis to know na nagsagot na kayo. Kasi nga, hindi namin na-access kung sino yung nag-evaluate sa amin. So, at saka makikita pa lang namin yung resulta a semester from now at least. So I don't have any way to know whether you submitted your evaluation or not. The only proof that the only indicator to me ay yung sagot nyo kay Canvas. So by 11:59 mamayang gabi, hindi kayo nag-yes dun sa quiz kay Canvas, you'll get a 0 out of 5 doon sa evaluation. I hope that's clear. So walang sisihan na, hindi ko extend yung deadline. So make sure after you answer SET, go back to Canvas, answer yes to get the 5 points. All right? So with that, guys, thank you for joining me today. Enjoy the weekend. Good luck sa mga mag-exam sa 151 on Monday. And let's see each other again on Wednesday. Bye, everyone. Oh, did I press record? Oh, thankfully I did.